Um, Hi, everyone. This talk is about digital signatures and how they work in Metamask. So this is going to be a bit of technical topic. And yeah, a bit about me. I'm Jyoti Puri, and I'm tech lead of Metamask confirmations team. Our work at Metamask involve transactional pages and signature request pages. Basically, any confirmation page that you see and use within Metamask is our area of work. Uh, in this talk, we'll talk about what are digital signatures, how do they work, and what's the math behind them, and the role of digital signatures in blockchain, what are the different use cases that digital signatures enable. Then we'll look at the various signing methods, from ETH sign, personal sign, to sign type data, sign in with Ethereum, and what's new and upcoming EIPs for signature requests. Now, to begin with, what are digital signatures? Now, the use of signatures to verify documents date back to 17th century. They have been used for a long time. Now, digital age has changed the means of communication, and thus the means of signing has also changed. And digital signatures are used to sign digital messages. And digital signatures actually cryptographically link a message to an identity. And digital signatures are based on algorithms. So how does it work with blockchains and cryptography is they use public key cryptography. So by that, if a user, Bob, is signing a message using his private key, then nobody can derives Bob's private key, and nobody can forge a valid signature for them. But anyone who has Bob's public key can verify that the message has been signed by Bob. Thus, Bob is able to verify his authority. He's able to prove his authority by using his private key and using that private key to sign signatures. Now, a bit of math behind digital signatures and how does that work in Ethereum. So digital signatures are derived using algorithm, and Ethereum uses something called elliptic curve digital signature algorithm, or ECDSA, to sign messages. Now, using ECDSA or an elliptic curve point manipulation, a value can be derived which is not reversible. So we can derive a value and we can verify a value. So this is like unidirectional operation. The value can be verified, but anyone with the signature cannot derive back the message or the private key of the signer. So a signature is represented by a tuple of 3 values, RSV, and it is stored as a 65-bit long sequence of characters. Now, the role of digital signatures in blockchain. Now, digital signatures are building block of blockchain. So if you are doing something very basic as submitting a transaction to blockchain, you need to sign it digitally to verify your authority for submitting that. Besides submitting transaction, a very important use case of digital signature is signing messages. So digital signatures can be used to sign any arbitrary messages. And by signing a message, a user is proving on the other end that they are actually who they claim to be. And to be able to sign any arbitrary message enables a lot of use cases, like signing transaction offline and then sending to the chain later, or pre-authorized agreements which can be finally settled by a third party, or somebody submitting a transaction on behalf of a user that the user doesn't have to pay gas fees for transaction. And this can also be used to achieve cases like scaling up the transaction settlement on chain, etc. Now, what are the different signing methods? So if you use signature request on MetaMask, you see there are a couple of different signature request UIs. There are actually a few different signature request methods, and there are a few different EIPs, which we'll discuss now. So these are ETH sign, personal sign, sign type data. It has a few versions, version V1, V3, V4. Yeah, MetaMask supports all of these. Now, ETH sign is the earliest type of digital signature. and it allows signing any arbitrary hash, and thus this is the most dangerous kind of digital signature, because a wrong actor can make you sign just any hash, which might be a transaction or something dangerous. So, and recently a lot of scammers have been reported to be using this. If you're using Metamask, we actually warn the users before they sign an arbitrary hash. And in the last release of Metamask, which went out this February, each-sign has been disabled by default for all the users. So if you want to use each-sign, you need to go to the settings to enable it. To overcome these security issues with each-sign, personal sign was spec'd. It's based on EIP 191, and how it differs from each-sign, there are mainly two ways. One is the hash is prefixed with a text called Ethereum signed message and length of the message. So nobody is able to hash a transaction and make you sign a transaction if you're using personal signature. Additionally, personal signature allows showing human-readable text. So if you're using Metamask, you'll see this human-readable text like this. It's like example personal signed message here. This text is displayed to the user, and as users sign, Metamask will derive the hash out of it and assign it using user's private key. It turned out that personal sign was expensive, and we needed, it was required to have something a more structured data to have more meaningful dApp interaction. And thus, signed type data was proposed, which is EIP 712. What happened with signed type data is the proposal kept evolving while keeping the same name, keeping the same EIP 712. Thus, some hard-coded versions are used for signed type data V1, V3, and V4. V2 is an intermediate, is left for an intermediate implementation by Cypher browser. Now, signed type data allow user to sign data which is more structured, at the same time more human readable. And the major design considerations behind EIP 712 was it should be cheap to verify on-chain, and should be human readable, and it should be hard to phish the signature. We'll walk through the different signed type data version. Signed type data V1, the data looks a simple JSON-like structure as this, where the user can specify type of the data, a label for the message, and the actual data which the user is signing. In Metamask, we display the message like this, which is very human readable, so you can read and actually sign the data. But a signed type data V1 had some security issues, and those were improved further in signed type data V3 and V4. So V1 should not be used in favor of V3 and V4. Signed type data V3 is very, very useful. It's very secure. It's very popular. What it requires is that the user, it requires the dApp to tell a scheme which they have used for encoding the data, to specify the structure of the data, and also specify the domain separator. So two dApps can have same data structure, but for the user to be able to be sure that they are signing the right message, they should be able to know what's the contract, what's the domain which is sending this signature request. So that's also enabled with signed type data V3. A signed type data V3 message looks like this, where the first section, in the first section, the user, the message the type of message is specified, the type of domain separator, actual message, and the structure of the message is specified. The second part of the signed type data request is the actual message, which is a JSON kind of structure. And a very important part of this is the domain separator. So when the request comes to MetaMask, we show the structured data like this, which the user can read. Also, we show to the user the contract from where it's coming. So you can actually go to either Etherscan and verify that you are signing the right contract. It's very secure, and it's the most popular and recommended way signature request method now. Signed type data v4 is actually very similar to signed type data v3, just the underlying libraries used are different, and signed type data is using more performant libraries, which are Metamask eth-sig-util module. And now, a recent addition to signature request is sign-in with Ethereum. Sign-in in Ethereum is based on EIP 4136, and what it allows is the user to authenticate itself to off-chain services by signing a standard message which specifies the scope and the session and the security mechanism. This is an alternative alternative of self-custodial authorization, and when comparing to centralized auth systems. Metamask has recently added support for this. Not just this, like for every signature request, for us, security is an important consideration. So if you're on Metamask and we find that the sign-in with request is coming from a wrong domain, we alert it to the user. So reducing fund loss incidents is a very, very important priority for us. And at every stage, we warn the user about it, and we try to ensure that users don't take the wrong decisions. And what's next? We keep Metamask updated to the latest EIPs and what's coming. So, and this week we have been discussing in the team about EIP 6384, which we'll prioritize to implement soon. What this EIP allows is that, so even though signed type data is pretty human readable, but still this EIP allow more user-friendly messages. So user can just read the message very easily, and this message has to be provided by the contract. So a contract needs to have this method of eval EIP 712 buffer. So the wallet will call this method. It will get the human readable string and display to the user, and so the user can make a more informed decision about signing the request. Yeah, so that was it about the signature request methods. So we looked at what are the digital signatures and how are they computed, and their significance and the use cases and the role in blockchain, and the different signing methods and sign-in with Ethereum. Now we have a bit of time for any question and answers. Thank you. Thank you.